Swayam Prabha. Digital India. Educated India.
Okay, great. So let's look at this very famous protocol. So quantum key distribution. Okay, and this is a very famous protocol by Bennett and Broussard. Okay, all the way from 84. And as I already said, it gives us information theoretic security. So that's its main claim to fame. So what is our setup in key distribution? Who remembers? How do we model the problem of key distribution?
We have two parties and there's a eavesdropper.
That's exactly right. So we have two parties. They're traditionally called Alice and Bob. Okay. So this is Alice, right? This is Bob, and they have a channel between them. Okay. Okay. And we have a channel between them, and we have an eavesdropper, right, who's listening to this channel. I don't know how to draw an angry face. Okay, let's not. So this is looking too happy. Okay, whatever. So this eavesdropper is listening to this channel, and what we would like to do is we would like the two legitimate parties to exchange a key, which they can then use for their future communication. So in class, in this course so far, we saw one by the famous Diffie-Hellman key exchange. We did not see one by lattices, not in so many words, but the lattice based encryption scheme that we saw can actually be adapted to do key exchange as well. You can figure that out on your own. So now we have the same problem set up, but now this channel is a quantum channel. Okay. And Alice, Bob and Eve, they are all quantum algorithms now. Okay. It will turn out that for this particular protocol, we also need Alice and Bob to share an authenticated classical channel. So let me draw that. Maybe I will draw it with a different color, just to specify that this is a classical channel. Okay, so this is a classical channel. And this is authenticated. So what does authenticated mean? Well, Eve can still eavesdrop, but if she tries to tamper anything, then this is something that will be detected. So there are various ways of doing authentication in cryptography, like digital signatures is one of them. We didn't have time to see that in this class, but it's very natural to think that you could do authentication using some kind of cryptography. It may require itself some kind of key to be shared or something like that, right. So let's not get into how this authentication is done. We are just going to say that there is a classical channel. So a classical channel is obviously much weaker than a quantum channel, and Eve can eavesdrop also on that, but if she tampers it, it will be detected. If in case they need to have a shared key in order to do this, then this key distribution protocol will be more like a key amplification protocol. So that means that fine, they started with some setup already, right. So they needed some setup to establish this classical authenticated channel, but whatever they do on top of that will sort of help them get a much longer key, and that too perfectly secure. Yeah. So that is our assumption. Okay, and on the quantum channel, this adversary has much more control. So, you know, she is herself a quantum adversary, so she could, you know, measure states that go between them, or she could try to delete something, or she could try to modify something, or she could try to send something new. Okay. So, one very simple attack that you know, one always has to worry about in this kind of a setup is the so called person in the middle attack, okay, wherein what you do is that, you know, you sit in the middle, you pretend to be Bob to Alice and you pretend to be Alice to Bob, right. So, this is something which, you know, we will have to handle. So, maybe we can use our authenticated channel for that, you know, because if there is a signature attached to messages, then, you know, the attacker cannot modify that without being detected. So, whatever way we will use, I am just pointing out that that is one sort of universal attack strategy that needs to be handled. Note that that is never an argument that, you know, a scheme is secure. Like, just because we foiled one attack strategy does not mean that all possible attacks are gone. So, this is just an example. Okay, so now suppose you wanted to do, you know, information theoretic key distribution in the classical world, okay, then we do not know how to do it, right. So, we have used computational assumptions. Now, in the quantum world, we will see how to do it. Are there any ideas? So, maybe it is nice to try and sort of build a protocol. So, let me maybe give some hints. So, we would like Alice and Bob to exchange some random string, agree upon some random string. What is the output of the protocol? A long random string which both of them agree upon and Eve has zero idea about, right. That is information theoretic security. So, what are ideas that you could think about? Yeah, very good. So, even to me, the most natural thing to try is, you know, entangle bits and then send them across the channel. So, yes, that is a strategy. In fact, what we will do can be seen from the frame of entanglement, but we will do it a little bit differently because we will follow the original protocol, but there are follow up protocols that like one by Eckert, for instance, which uses entanglement explicitly. We will not use entanglement, but it is a very natural idea. What we will use, the key idea that we will use is that you know, you could measure in different bases, right. So, in particular, there are two bases that we have studied quite extensively. One is the standard computational one, right, 0, 1, and one is Hadamard. So, if I send you some bits encoded in random basis, right, then the point is that if I do not tell you immediately what is the basis that I used and I simply send it to you, right, then what can Eve do? If Eve does not know in which basis to measure, then whatever basis she chooses will be wrong with some probability and she will end up disturbing the state. This is the main idea that we are going to use, and actually it turns out that the protocol we will see, it is a very natural and nice one. We will in fact not in class see a proof of security. So, it turns out that the proof of security is quite complex and it was actually provided 12 years after the original protocol was provided. Okay. So, in class let us just look at the protocol itself and just reason about security without formally proving it. So, in the interest of time, let me go ahead with showing you the protocol. Okay. So, before writing the protocol, actually I want to talk about the main idea, right, the main property that we want to use. The main property is that if a bit B is encoded in an unknown basis then Eve cannot get any info about B without disturbing the state. And if she does something like that, if she disturbs the state, then Alice and Bob can detect it. Okay, this is the main property that we are going to use. Now, let us look at the protocol. How will we use this idea? So, Alice chooses n random bits A1 to An, okay, just think of n as some large number. And also she chooses n random bases. So, Bi is, you know, it is either computational or Hadamard. I hope this makes sense. Okay. So, I am choosing actually two sequences of bits. I am choosing two random binary strings. The first one corresponds to the bits that I want to exchange. The second one corresponds to a random choice of bases. Okay. So, if it is 0, it is computational, if it is 1, it is Hadamard. Okay. Okay. So, now she sends Ai in basis Bi. Okay. So, what does this mean? So, you know, if Ai is equal to 0 and Bi is equal to 1, then what does she send? So, remember, you know, we have let us make sure we understand this, right. So, this is our you know, B equal to 0 and B equal to 1. Okay. So, if B is equal to 1, that means I will look at the Hadamard basis. Okay. And if my bit is 0, I will pick plus, if my bit is 1, I will pick minus. Okay. So, I am going to send plus over here. Okay. Now, do you already see how mixed states are coming in? Can anyone connect this immediately to the mixed state idea that we saw? If I want to transmit bit 0, then with probability half I pick plus, and with probability half I pick 0. That is exactly right. Okay. So, it is a mixed state. Yeah. So, good. So, step 1 is clear. We choose two random strings, and the first random string we send in terms of the basis specified by the second random string, bit by bit. Yeah. Okay, very good. Now, before I tell you step 2. So, you know, we have already made a lot of progress, I claim. Now, let us just think about what is happening. So, you know, I am Alice, I have already sent you this. Okay. Let us say that, you know, you have received it, you are Bob, and maybe you are Eve and you have eavesdropped on it. Now, as Eve, what can your strategy be? Now, you are seeing some, you know, random quantum states going by, right. You do not know what it is. I mean, so this is a quantum state, right. So, you have no information unless you measure. Now, which basis should you measure it in? If you measure it in the wrong basis, then you will collapse the state, right, to something you know, to something else, and this will disturb what is being sent. Now, suppose you do that. So, suppose I measure everything and I get some values, right, and I proceed to send these measured states along. then how can such a strategy be detected? Yeah, that's a very good question. So the question he is asking is that, do I send the the bits in the classical channel? What do the bits of the basis in the classical channel? This is the question being asked. So what do you all think? Quantum channel, classical channel? Actually, the very nice thing is that it's using a very crucial thing about quantum over here. What is it using? It is using the fact that the quantum state is a physical object, right? If you tamper it, you disturb it, okay? If you don't tamper it, you don't have another chance. This is a very important thing. So, now about the bits of the basis, do I send them or do I not send them, okay? So, there are two ways to do it. Either you can say that let Bob measure in a random basis and later we will reconcile. So, suppose Bob measures this received string in a random basis, each bit in a random basis, then in expectation how often will he choose the correct one? Half the times. So, you could later Bob could send over the classical channel to Alice. Actually, this classical channel, don't worry about it very much. We will see what role it plays. But think, when I say don't worry about it, I mean just think first in terms of the communication that is happening. Okay. Now, if I send back to you what basis I measured it in, you can then tell me that throw away these positions, these were wrong. You could tell me that, in which case at this point I know hopefully that I have I measured in the correct basis. So, at least if Eve has not tampered, I got the correct thing. I need to still do something to ensure that Eve has not tampered. The other possibility, this is one possibility, the other possibility is that Bob doesn't measure in a random basis, but Bob simply sends a message saying, I received everything. You sent me n things, I received them, now you tell me which bits to use in the measurement. This I find very cool, right, because now if Alice sends the whole bit string, there is nothing Eve can do. This is actually like a key thing which is making it very different from classical. See, with classical, right, when we work in cryptography, we see that in some sense the attacker and the legitimate party are always on an equal footing. But here the temporal aspect comes into play, which never happens in classical. Now, previously in classical, if I sent the secret basis, right, then everybody knows it, Eve also knows it, and now whatever had been sent before, she can do something with it. But now because what was sent before is quantum, Eve cannot actually do anything. So, now this information is useless to her, very roughly speaking. Okay. So, the second possibility which I was saying was that Bob simply sends an acknowledgement that I received everything, and then Alice will send the random basis string. This is another possibility, in which case I do not need to throw away half the positions. But why do we often not do that? So, this protocol can be described in either way. You could say that he measures it in a random basis and then they agree which ones to throw, or you could say that he simply sends an acknowledgement and then she sends the full basis and then he measures. The reason that often we think of Bob just measuring in a random basis is again quantum. Storing quantum bits is not so easy. So, you see the sets of powers and the sets of limitations are different. So, in classical, you sent it, no problem, I mean I can keep it for any period of time, but here oftentimes from the experimental point of view, it is important for me to measure it soon after I get it. I cannot kind of keep it for too long. So, that is another consideration. Okay. So, yeah, you could look at it in either way. I will just have Bob measure, measure in random basis. So, that is step 2. So, Bob chooses some random bases B1 prime up to Bn prime, and measures the received qubits in these. Okay. So, now he will get some A1 prime up to An prime. And now Bob sends all the Bi prime to Alice, and Alice sends Bi to Bob. Okay, and for the matching positions, if Eve did not tamper, right. Okay, so now based on what we have seen so far, Eve actually could have made mischief, isn't it? So, this person in the middle strategy applies, right. So, let us say Alice is sending the quantum stuff, Eve sits and measures it, right, and sends in some random basis, and then sends the resultant states to Bob. Now, Bob sends the B's, okay. Alice sends her version of the B's, and at this point Eve actually has full information, right. Eve knows what B's Alice used, she knows what B's she used. So, she is like a Foony Bob. So, she can now have a shared key with Alice, and Alice and Bob are actually left with incompatible keys which they do not know about. So, how do I try to thwart this simple strategy? What can I do? Yes.
Alice should somehow be able to verify what are measurements Bob made.
Good. So, the suggestion is that somehow make Alice verify the measurements, and indeed we will do that, and we will do that in fact the simplest possible way, which is that for some random set of the remaining bits. So, now there is some set of bits where the measurements agreed. In that set we will choose another half of them where actually we will communicate what values we got also. Okay. So, now I mean intuitively, of course, this will thwart the attack that I was talking about with high probability, right, because if I am, it is clear, right. I mean if I am going to verify the bits that we recovered, then any tampering that Eve may have done should get detected by this. Okay. So, let me write that down. So, now Alice selects n by 4 locations in the shared string and sends Bob the AI and these locations. So, for all these locations Bob will get what bits she had transmitted, and now Bob can verify that these are the same with high probability. So, we say with high probability because the channel itself could have caused some errors and so on. So, let us say we know what is the error rate of the channel. So, if we see more errors than what can be explained by the channel error rate, then we suspect that Eve has messed with it, right. So, if the fraction of errors is somehow high, however we want to define that, then they abort the attempt. Okay, and if not, they get n minus 4 shared bits. So, by sending n bits, we have ended up with potentially n by 4 shared bits. So, the question is, why can't Eve mount the same kind of attack? Because now if she is receiving these bits, then why can't she somehow again fudge the picture so that things look consistent between her and Alice, right? Like maybe whatever bits are being sent by Alice, right? She could change them to be something else or something like that. She could do something like that. So why can't she do that? Because at this point this is classical, so we can use our classical authenticated channel. So, if she tampers and tries to launch the type of attack you are suggesting, then it is going to get detected. That is the reason. Yeah, so the question that is being asked is that if, I mean, when we send this information, then Eve also can see it, right. So, doesn't this constitute some kind of leakage on the original string? And the answer is, there are two answers. One is that it constitutes leakage and therefore we will throw it away. And the second is that the reason throwing it away suffices is that you are assuming IID. So, if something gets corrupted, it does not affect the rest of the string. So, that is also an important assumption that we made. So, in hindsight, it is very natural, but I do want to say that all the discussion we have had so far is still very hand wavy, right. So, I mean basically we are saying that yes, there is some probability Eve can even get away with it, like let us say that she tampers only with a few bits, but the test bits do not fall in those, something like that, then yes, she can get away. But as usual, these will be probabilistic arguments where you will say that if she tampers very few things, then yes, she could get away with it with some probability, but then the rest of the positions are still alright, right. So, there is, I mean if she does more tampering, then the probability of being, the more damage that she does, the more is the probability that she will get caught. So, yeah, it needs a formal argument to say that in the end n by 4 bits are correctness is clear already, right, that okay, we agreed on n by 4, that is clear. It needs a formal argument to say that Eve did not learn anything at all. So far we have just made some hand wavy rationalizations. These do not constitute a proof of security. Next class we will still not prove security, but I have actually debated a lot about this, and in the end I decided that in the time we have remaining, I do not want to spend a lot of time proving the security of this protocol. As I said, it is a non-trivial proof which came only 12 years after the original protocol was suggested. So, next class we will just think a little more about security in the same informal way, but then we will move on to doing encryption and so on. Okay. So, I will refer you to some notes if you are interested in reading about the full security proof.